there are two types of errors you can make with these analyses. Type 1 error is a false positive. So you're mistakenly rejected the null hypothesis in favor of the alternative hypothesis. So in the example that they're giving here, this is one of the first times I've laughed at something a statistician made. So a type 1 error would be saying to someone that they are pregnant when they are in fact are not pregnant. And they give a really obvious example here, telling a man that they're pregnant is obviously going to be the type 1 error. The type 2 error is a false negative. So that is saying you are not pregnant when you actually are. So then they show a woman who is clearly pregnant, and that would be telling her that she is not actually pregnant. So that's a good example, and I'm going to go over another one as well. So you should always pay attention to what types of errors are most important in your particular example. I'm going to give an example of mammography here. So errors in mammograms to detect breast cancer. So mammograms actually have a pretty large amount of error for a normal test or medical test that they have. But even given that error, it still provides value. So it's a great example to think of this false positive and false negative dichotomy here. So the false positive rate, so that would mean that the patient does not have breast cancer, but the doctor told them that they did have breast cancer. So it would be an incorrect positive or false positive. That with mammography happens 7 to 12% of the time, and it's more likely to happen in younger women. So I'm sure they use some type of statistical test and try to predict how to come across the least number of errors. So that would be a great application that I'm sure this is used for. So they have a cutoff. It's either, I think it was 50 and they moved it to 60, or maybe it was 40 and they moved it to 50. So they actually made the cutoff for recommending a mammogram later than it was, because they were getting so many false positives on younger women who are less likely to have breast cancer in the first place. So that is one type of error. This type of error, the result of that would be biopsies that you don't need to do, but expensive medical tests that you don't need to do. But someone's probably not going to die as a result. So a false negative happens about 13% of the time. This means that the mammogram is negative and the patient actually does have cancer. That's what we really want to prevent in this case. It's very clear that we would want to prevent that specific outcome, because a false positive is not a good thing, but nobody's probably going to die as a result. Whereas a false negative, it's very possible either that they may die or have a way worse cancer when it's actually correctly diagnosed. So every time that you do a statistical test, you need to think about, okay, what type of errors are really bad in this situation, and then modify it in order to try to not get that particular result. And I can give an example when we go through our example. So this is what I've already gone over. So yes. So just a real quick review of statistical significance. The goal of all of this is to have a statistically significant result. So this means that our results were so extreme that you're trying to pick to detect a difference. They're so extreme, one group versus the other, that it's almost, it's very likely that it didn't occur by chance. So we quantify that using p-values. So what this means in practice, a p-value of 0.05 is usually what we use in a statistical test. You can vary that based on your use case. I'm actually going to give an example of when you would want to vary this, but so you would want to use that 0.05 as a cutoff, and if you're thinking of it, like we said last time, in terms of z-scores, it would be 1.96. It would be the z-score cutoff for that. If you don't know what that means, you may want to go back in the materials review. So other cutoffs that we would use are 0.1 or 0.01. So in practice, a 0.05 alpha value or p-value means that if you reran the test again and again, there's a 5% chance that your particular conclusion would have happened in error or mistakenly. So just because you're taking samples, it looks different every time. Therefore, sometimes you're going to get it wrong. And 0.05 is saying that you'll probably only get it wrong 5%. So we already talked about this, but this is how you would change your statistical test in order to account for your different levels of error. So your tolerance for error, when you're looking at a breast cancer technology or tool to detect breast cancer, the one that you really want to pay attention to is going to be that false negative. So you would want to, in this case, when lives are at stake, you have a smaller p-value, so you would do 0.01 instead of 0.05, just because it's very important that you get it right. So you would want a 1% chance of error versus a 5% chance of error. So your threshold for error is going to be less or more in this particular